Okay, press it.
Okay. All right, you guys. It is time to learn new stuff. So far, we've been dealing with electrical circuits that only have two elements, right? A battery and a resistor. And you guys end up doing V equals IR to answer questions about it, okay? But now we're going to start learning about more complicated circuits, circuits with multiple resistors, and resistors connected to each other in weird, multiple ways. And then we'll finally be dealing with circuits that have multiple batteries in them. And as we go, we'll learn more and more techniques how to deal with more and more complicated electrical circuits. Well, today is the beginning. We're going to deal with resistors in a series. So let's start. Hold on, my phone's ringing. Telemarketer. Okay. Well, resistors in series. Okay. The first thing you need to know is what series wiring is.
Mr. Shannon, how do you zoom this thing in?
Just a second.
It's on the top.
It's this guy like
Yes, I see that.
Thank you. By the way, Noelle is our guest videographer today. Okay, series wiring says devices are connected so that each receives the same current. Devices are connected so that each receives the same current. Okay. We're going to start making pictures of electrical circuits, but I'm not going to make pictures of like a battery that actually looks like a real battery because there's so many different types of batteries, and I'm not going to make pictures that show what resistors look like, because even though most resistors look like that, you've got some resistors that look different. Instead, I'm going to use a generally accepted symbol for a resistor and a generally accepted symbol for a battery. So the symbol for a resistor looks like this. It looks like a jagged bunch of jaggedness. And so I think what they envision is you were like driving your car over a really rough road, and the rough road prevents your car from going fast. It like resists the motion of your car or something. But anyway, that's what we use to make resistors. And then batteries, we use this. You know how batteries are, anode, cathode, and electrolyte, and charge naturally flows from one to the other? Well, that's kind of, the batteries used to be made with plates, like a plate of zinc and a plate of whatever, copper? Was it copper and zinc, or zinc, lead and zinc? So a plate of zinc and a plate of lead alternating with an electrolyte in between, some sort of acid, and then you get your battery. And we usually put a negative and a positive just to make it really clear to everybody that this is the positive terminal and that's the negative terminal of the battery. Okay, so I'm now going to draw a picture of a circuit that has two resistors in a series. Here it comes. I have a battery. By the way, you can make as many little plates as you want. I tend to just make two plates because I'm lazy, but I've seen people who make a battery that looks like this. Like they just, can't get enough of those plates. But I don't do that. I just do two plates. Alrighty. And then I've got one resistor, and then another resistor, and then it comes down. This resistor I'm going to call R1, and this resistor I'm going to call R2. And this voltage source, this battery, I'm going to say it has a voltage of V. Current through a circuit is like water through a hose. Whatever water enters a hose has to exit a hose. If water is entering a hose at like 1 gallon per minute, then the water has to exit the hose at 1 gallon per minute. You can't have a situation where 1 gallon per minute is going into a hose, but 5 gallons per minute is coming out of the hose. That can't happen. And similarly, you can't have 1 gallon per minute into a hose and only a half a gallon per minute out, because where did the other half gallon go? Maybe your hose has a leak or some aneurysm or something, I don't know, but for the most part, whatever water comes in has to come out. Well, it's the same with current. Current is coming out of this battery, and whatever current is coming out of the battery must flow to every part of this circuit and then return to the battery. The current doesn't vanish. It doesn't just, go away. I mean, whatever many coulombs per second are exiting the battery has to eventually enter the battery again. Re-enter the battery. And so these two resistors are said to be connected in series because whatever current enters and exits this resistor must enter and exit that resistor. It has no other choice. There's nowhere else for that current to go. And so these two resistors are in series. We could hook up our entire classroom in series. We would just stand around the perimeter of the class, and I would grasp with my left hand, I'd grasp the right hand of a student and grasp the left hand of another student, and we would go around. And then we would all be in a series. Each of us only connected to 2 students, one on each side of us, with a different hand. And then if current flowed through one student, it would flow through all of us. You guys okay with that? Okay, great. Series wiring. Let's talk about Ohm's law. Look here, I've got a current going through R1. That current has a certain amount of electrical potential energy. But when that current passes through R1 or fights its way through R1, through that gauntlet, it's going to give up some of its energy. How much of its energy? Hey, Ohm's law tells us exactly how much. Ohm's law says the voltage drop, which is the amount of electrical potential energy per coulomb that this charge is going to lose, is given by Ohm's law, V, and I call that V1 because it's R1, V1 equals I R1. That's how much energy that charge is going to lose per coulomb. Whatever the current is multiplied by whatever the resistance is. So whether this is a light bulb or a motor or even just a heating element, something that gets hot, this current is going to give up its energy in order for it to do what this element wants it to do. Turn a motor or get hot or light a light bulb. And the same thing's going to happen here. You're going to lose more energy. It's going to enter, this charge is going to enter R2 with a certain amount of voltage, a certain amount of electrical potential energy per unit charge. And then that charge will give it up when it passes through R2, and then the charge will return to the battery. And the amount of energy it gives up, I'm going to call V2, which is I times R2. I'd like to make I'm going to get a quick drink of water. I'd like to make an analogy with a waterfall. Here's a waterfall. Here's like a water wheel right there. Here's some water wheel right here. Okay. I've got a bunch of water here. This water has gravitational potential energy. This water is going to fall, and it's going to turn that paddle wheel, and then the water comes here. The water has lost gravitational potential energy, but it did turn the paddle wheel. You got some work out of it. You got something productive out of it. In the same way that this charge here has a lot of electrical potential energy, and then as it passes through this resistor, it loses some of its electrical potential energy, but you got something out of it. You lit a light bulb, okay? And then this waterfall comes here and falls, and turns that paddle wheel and comes here in the same way as the charge does something for R2. But is that it? Does the water just sit there? Is it done? No, the water keeps flowing. This is a river, you know? So the water keeps flowing, right? And in fact, if you want these water wheels to turn, you need that water to keep flowing. If someone dams up this waterfall here, or even dams it up here, so that somehow maybe the water would rise and now it's just all underwater, or I don't, it's hard with this analogy starting to break down, but I just want you to know that if you stop the flow of water, then these guys aren't going to turn anymore, because they're depending on new water constantly falling and turning them. If you stop the flow of water, then that's it. They're done. They're not going to turn anymore. And the same thing with current. And even if I put my open circuit right there, if I put an open circuit right there, then no more charge is going to flow. All the charge gets backed up, and then you don't get any more voltage drop across those resistors. Because this charge entered the resistors, gave up its energy, and is not being replaced by new charge. So let's get this back. All right. Well, now I'm going to go mathematical, and this is like the easy part. Here we go. I've got two resistors in series, and that voltage here, whatever voltage whatever energy the charge starts with, it's going to lose some of its energy here, lose the rest of the energy there, and then limp back with 0 volts of energy. So here the voltage is V, here the voltage is 0 volts. It gave up all of its energy in going through those two resistors. And so I can say that whatever energy the charge started with was lost in these two resistors. So it's going to be equal to V1 plus V2. Started with a particular voltage, lost some of it, lost the rest of it. And when I say voltage, I mean electrical potential energy per unit charge. But by Ohm's law, V1 can be replaced with IR1, and V2 can be replaced with IR2. And so I can factor out the R, and I get R1 plus R2. Well, this is looking like Ohm's law, right? V equals IR. But it turns out that the resistance the battery sees is equal to the sum of the resistors in series. And the same thing would happen even if there was a third resistor. If I had a third resistor, R3, then he would have a voltage drop, and I'd have a V3, and I'd have an IR3, and now this would be R1 plus R2 plus R3. So I want you to get that when I have resistors in series, the equivalent resistance, the resistance the battery feels, is just the sum of the resistors. Because there it is, V equals I, R. So the equivalent resistance of resistors in series is just the sum of the resistances. It's that easy. So hey, I'm going to do a problem for you. Then I'm going to have you guys do a problem. Then I'm going to be done. Yes.
So with each resistor, the resistance increases.
Yes.
So until it reaches 0, or eventually at the end it reaches 0, the voltage. So like with so R2 would have more resistance than R1, and R3 would have more resistance than R2.
No, you can still think of them as individual resistors, but it's just, but definitely the resistance the battery sees gets increased with every new resistor you put in there. Yeah, so in that respect, it's like you know, a family where every new kid they have costs more money, you know, for the family, even though it might be cheaper. Maybe it costs you less extra outlay for your 5th kid than your 1st kid because you've already got a lot of hand-me-downs and, you know, economy of scale or whatever. But still, every additional kid, you're going to have to spend more of your money now to care for your family. And that's kind of what's happening here. I don't know if that's a good analogy. But there you go. Okay, hey, let me do an example. Here's example 1. Please draw this circuit. This is a 12-volt battery. This is a 20 ohm resistor, and this is a 10 ohm resistor. And then it comes back there. Please draw that circuit now. Okay, I'm going to answer the following questions. Number 1, I want to know what the equivalent circuit resistance of the circuit is. I want to know how much resistance that battery feels. Number 2, I want the current that's coming out of the battery. What current is the battery having to provide this circuit? Part C, I want the voltage drop across R1 and across R2, or I guess I should say across the across the 20 ohm resistor and across the 10 ohm resistor. And then finally, part D, I'm going to designate 3 points, V1, V2, and V3, these 3 points in space, and I want to get what V1 is, what V2 is, and what V3 is. And like I said, I'm going to do this problem. And then I'll give you guys one to do just like it.
Yes, it does. That's
But you're discovering more and more about
well,
this.
I'm trying to figure out why it's so tall.
Oh, yeah, yeah.
Cause like I don't know. Cause yeah, the
Okay.
part D is not on the screen, and I don't know how to fix that.
Okay, good. All right, here we go. First of all, what resistance does the battery see? Hey, he sees the sum of the 2 resistors because they're in series, right? Whatever current enters and exits this resistor has to enter and exit that resistor. So they're in series. And resistors in series just add together. So this is going to be 20 ohms plus 10 ohms for a grand total of 30 ohms. That's the resistance the battery feels. Now, the battery doesn't know how the resistors are configured or divvied up. For all the battery knows, it's a 10, a 10, and a 10. Or maybe it's a 5, a 10, and a 15. Or maybe just a single 30 ohm resistor. But regardless, the battery feels 30 ohms across its terminals. The current out of the battery, you're going to have to do V equals IR, or I equals V over R. And so I got 12 volts over 30 ohms, and that's 0.4 amps. So that battery is having to deliver 0.4 amps of current, which means 0.4 amps of current is coming out of the battery, and 0.4 amps of current is coming back to the battery. That current's not, going anywhere. It's just, it's not disappearing. It's 0.4 amps. That's what you got going through it. The voltage drop across the 20 ohm resistor, I've got 0.4 amps going through a 20 ohm resistor. How am I going to find the voltage drop across that 20 ohm resistor? What's that? Yeah, multiply them together. Ohm's law, V equals IR. I hope you see that that 0.4 amps of current is going to be giving up 8 joules of energy for every coulomb that passes through that resistor. Because the voltage, IR, is going to be 0.4 amps times 20 ohms, which is 8 volts. So the voltage drop across the 20 ohm resistor is 8 volts. I hope you see that I've got 0.4 amps going through a 10 ohm resistor, so your voltage drop is going to be 4 volts. That is, whatever energy, per coulomb your charge has when it enters the 10 ohm, it's going to exit it with 4 joules per coulomb less energy. It's going to lose 4 volts of electric potential. And then finally, getting back to our definition of voltage as a characteristic of a point in space. Right here, we designate the negative terminal of the battery of being 0 volts. And we say the definition of a battery is this point here is always going to be 12 volts higher than that point. That is, the positive terminal is always kept 12 volts higher than the negative terminal. Because this is a conductor, every point on this conductor will have the same voltage. Till we reach this point here, that's still going to be 12 volts. But I'm losing 8 volts. So every coulomb of charge here has the capacity to do 12 joules of work. But now that charge passes through the 20 ohm resistor, loses 8 volts of electric potential, that is, loses 8 joules per coulomb of ability to do work. You tell me, how many volts is it at V2? How many people thinking 4? Yeah, you had 12, you gave up 8 in lighting that light or heating that element or whatever, and now you've got 4 volts. So this guy is going to be 12 volts, this guy's 4 volts, and what's V3? What's this voltage here going to be?
0.
Yeah, 0, the same as the negative terminal of the battery. You lost your remaining 4 volts and it's now 0. Any question or problem on this before I give you one to do on your own? Alrighty, then hey, here it comes. Please draw this schematic. Okay. This is 10 ohms, this is 10 ohms, and this is 20 ohms. And this is a 20 volt battery. Go ahead and please answer the same questions, except it's going to be V1, V2, V3, and V4 here. Good luck, you guys. Good luck. Get the equivalent resistance, the battery, and the Is everyone here today? Yes. Yes. Is anyone having difficulty doing any of these problems? If you are, let me know. No way. Oh my God. These are my famous books. They. Oh my God. These are all for you, right? These are like the classic books. Hitchhiker's Guide is awesome. I love that book. Good for you. Man. Except for Mein Kampf. I could never, I read like 5 pages.
Yeah, it's still a lot for me, but I'm a history.
Yeah, right on. Yeah, there it is, man. Okay, you guys ready?
No.
No? Okay, I'll wait. Let me look at something. Yep. I'm going to put you on camera. Oh, please, Noelle. Please, Noelle. She's doing such a... Imani, yay. Have I ever pointed this at you guys? It's just me, right? Hey, happy students. You guys are like such a good class. Oh, I'm so happy with you guys. And then Noelle has her head down. She's so cute. You have a beautiful face. Why do you hide it with that hair?
You showed your calc class before, but not this.
Oh, did I? Oh, good. I'm glad. Yeah, because this is it. I mean, this is going to have to do me for the rest of my career. I really don't know how to videotape my lessons again. So for the next 10 years, man, this is it. You guys will be in suspended animation. In 10 years, you'll be a 28-year-old fat housewife with 5 kids.
Say that.
You'll be able to look back on this. I remember those good days.
Hey, I'm ready, Mr. No, I'm talking about.
Okay, so are we ready? Let's do it, man, because we're like running out of time. Okay, first of all, I hope everyone got that the equivalent resistance is 40 ohms. How many people got that it was 40 ohms? Okay, yay for you guys. And so now the current out of the battery is going to be 20 volts divided by 40 ohms, which is 0.5 amps. How many people got that? V equals IR, awesome. Now, let's go ahead and do the third thing. Let's get these voltage drops. Hey, if I've got 0.5 amps going across that 10 ohm resistor, that's a voltage drop of 5 volts. And that same 0.5 amps is going through that 10 ohms, 0.5 times 10, 5 volts, 0.5 times 20, 10 volts. So it's 5 volts, 5 volts, 10 volts. How many people got that? Okay, good. Good for you guys. Awesome. And then the last thing is this. We know here it's 20 volts, and we know here it's 0 volts. So right there, V1 is going to be 20 volts as well. What's V2? What's the voltage at V2 going to be?
15.
Yeah, 15. You had each coulomb had 20 joules of energy. They lost 5. 15. What's the voltage at V3?
10.
Good. And what's the voltage at V4?
0.
0, which is the same as there. Okay. Any questions or issues on this? This is the level of knowledge I need you to have. There's one more thing I need to tell you, though. Chemists know that it is negative charge that flows. Electrons are the electrical fluid, correct? But physicists and engineers, evidently we don't know that. Because from now on, whenever I talk about current, I'm talking about the flow of positive charge. In fact, everything that's done in electronics almost presupposes the flow of positive charge. Even though we know that doesn't happen, in the back of our mind, we know that's not really what happens, right? But from now on, that's the way I'm going to treat this. So this charge, this current that we got going here, these are positive charges. You see? And the charge that's giving up its energy to light the light bulb or turn that motor, these are all positive charges giving up its energy. Because the direction of current is the direction of flow of positive charge. And that's the way we do it in engineering and physics. All right. Hey, any last questions on any of this stuff? All right, then one more thing I got to tell you. Tonight's homework, it may look like a lot, but the problems go very fast. The first 4 problems are resistivity, the next 4 problems are power equals IV stuff, and then the last 4 is what we just learned. Okay, so are we ready to say bye-bye?
Press the red button again.
Yeah, press the red button again.